Basically,
Okay, welcome everybody. This is going to be our table week, right? We'll be talking about Tabular data visualization today and on Thursday. And so just to hark back a little bit to the data set types that we introduced in like one of the early lectures when we talked about data. Remember, we have tables, networks, field, geometry, clusters, sets, and lists. And like this week, we'll really be digging into Tabular data visualization. Tables are made up of items and attributes. We have two-dimensional tables, or we could have high-dimensional tables. And I want to kick this off by doing like a little exercise. And so the point of this exercise is really to just try to sketch those two tables, try to kind of like actually visualize the data, and then think a little bit about why did you choose different visualization techniques for each of those tables. Sure. You have enough? Yeah. Cool. Happy to. Can you, do you have an extra? Okay. Leftovers, thank you. Thank you. No. Sure. It's all like it's just 3 time points. Like in beats per minute is supposed to be heart rate, but it doesn't really matter if you mean the second data set. Let's take 1 more minute. Okay, so it doesn't matter if you haven't completely finished, but the point is you probably thought about how to visualize each of those tables, right? Which one was easier to find a visualization for? The second one, yes. Why? Exactly. We have homogeneous values, right? We have like the columns mean the same thing. What are some visualization techniques you chose for the right one? Exactly. A line chart is like a very good choice here. Anybody else? Exactly. So these are good options, right? Any other ideas? So yeah. Yes, of course. Yes, exactly. So yeah, the point of this exercise is, of course, that this is easy to do. What is the left thing? What any ideas? What did anybody come up with? Yeah. Okay. Yeah, so that's a cool combination. We have like a scatter plot that shows us a little bit. Maybe there's a correlation between speed and how far somebody can jump, right? It's not unreasonable to assume that we would see some correlation. And then we would also expect some correlation between gender and age, right? So that younger people are probably not as fast than the 22-year-olds. But yeah, that's a great idea. Anybody came up with a different idea? Yeah. Yeah, that would potentially work, but so then you have basically just like a parallel coordinates plot, right? So you have one line for those two people. And how do you do the gender and age? Okay. So one thing we could definitely go ahead.
I was just gonna say what I did was I forgot what it's called, but one of the flow like with multiple lines. And so each one is a continuous line of a single color.
Yeah.
And it like maps each one, and then the last one is just two categories.
Okay. Yeah. So that's a parallel coordinates plot, and we'll be talking about this on Thursday. So yeah, that's a good idea. So parallel coordinates plots, for example, are good for heterogeneous data like this. But generally, as you saw, you had to think a lot more about visualizing this data than you had to think about visualizing the other kind of data. And we'll be talking about all kinds of visualization for tabular data today. But what the point of this was also to think a little bit about the scale of tables. So we need different approaches for what we call normal, or what I call normal and high dimensional tables. So for example, how many dimensions, how many columns do you have? Do you have 50? Maybe you can just use a visualization approach, right? But if you have more than 1,000 or 1,000, then you need to do something different. You need to do something smart. You need some analytical methods here. And we'll be talking about analytical methods in a separate lecture, but I'll give you a few hints here. How many records, how many rows do you have? Well, if you have about 1,000, then usually just using visualization is fine. But if you have more than 10,000, we probably need analytical methods. This will overplot, right? We need to do something about this. But very, very important, and the point of this exercise here is the homogeneity of the data, right? So if I have numerical data of the same type for 2,000 by 2,000 matrix, I can probably just do a heat map, right? And I can still see it. But if I have something like the first table where we have different types in each column, then I'm probably screwed, right? I have to do something completely different. Think about that. So the homogeneity really matters a lot in terms of scalability. So whenever you think about the scalability of a visualization technique, you should also think about what kind of data are we talking about. So here's like this example. They have very different properties. And so what do I mean with analytical component? Here is like a spectrum from no to little analytical components to very strong analytical components. So on the left one, we have things like the scatterplot matrix, which is just like a combination of scatterplots or the parallel coordinates plot that we just talked about earlier. In the middle, we have a pixel-based visualization, a heat map. And that's actually, I can always render a heat map without running any fancy algorithms, but really to see any patterns, I have to use some kind of smart ordering, for example, a clustering method. And so if I use clustering here, I'm using a little bit of analytics to improve the appearance here. And then on the extreme here, this is like what you do if you have a ton of data, is you use approaches such as multidimensional scaling or dimensionality reduction or principal component analysis, right? Where you try to derive some higher level patterns analytically from the data set and then plot these higher level patterns. And so we'll be talking about all of these, but we'll also be talking about like the things here in a separate lecture when we talk about aggregation and clustering and so on. I earlier posted this cheat sheet from the Financial Times graphics desk. And I think this is like an excellent cheat sheet for tabular data visualization. So they kind of like think about the tasks in tabular data visualization, and they classify it as into judging magnitude, distribution, deviation from a reference point, correlation, ranking, part of whole, or change over time. And these are really the key tasks that you want to answer in when you analyze tabular data. And they have this kind of nice list here for which visualization techniques are suitable for each of them. And I'm gonna like loosely structure these two lectures based on this classification. So we'll start off with magnitude, and then go to distribution, and we'll spend a lot of time on correlation because of course correlation is a big topic. We'll talk about ranking on Thursday and so on. Okay, so you can download this, and this is like handy to have around, right? If you ever have to design a tabular data visualization technique, ask yourself, what do I want to see? What do I want to compare? What are the tasks? Then you can go into this chart, and then you can look at the options, and one of the options might fit your problem. So let's start off with the first one here. When I want to visualize magnitude, this is kind of the simplest one of it all, right? And this is like, I'm really mentioning this just for completeness sake. Basically, we can draw bar charts. And we also talked about grouping a little bit last time, and we talked about multiple views. We can group bar charts in different ways. We can do vertical and horizontal bar charts. I am very often partial to horizontal bar charts because, especially if you have more than a few, the benefit of horizontal bar charts is that you can like print labels nicely, right? If you have a lot of bar charts, you have to tilt the text or make the text vertical, which is hard to read. And this is also kind of like easy to scroll, right? Like if you have more than, let's say, 100 elements, you can scroll the bar chart, a horizontal bar chart. And then very related to the bar chart is the lollipop chart. This is just like a slight design variation. Here's like a comparison of different bar chart types. This is from like this, there's a series of articles that Nature Methods published in 2013 to 15. These are just simple one-pagers, and they give some kind of like visualization introduction. And this is from one of these series by my friends and colleagues, Mark Streit and Neil Scalenborg. And so we have 5 categories in our data set. And we could visualize this as a pie chart if you want a part of a whole relationship, or we can visualize it as a stacked bar chart, or as a layered, or as a group bar chart. So notice that these are small multiples, as we talked about this last time in the view, right? And so very clearly there's differences in like what these different things afford. So for example, here, the layered bar chart is really great for within group comparison, whereas the group bar chart is really good for comparison between the different groups within the items, right? So you would choose your grouping based on the tasks that you need to address. And of course, if you have, if these things are, like if these data values, for example, were sales by different offices for certain products, then you also might be interested in the overall sales by a certain office. And then having something like a stacked bar chart is, of course, a great thing to do. Here is like a tabular data visualization technique that I showed before, where we leverage these bar charts here. And also like in your homeworks, you're working on something like this, right? Where you have these bar charts and you can sort them by anything like that. Another way to visualize magnitude is what's called isotype visualization. This is kind of like, goes back to a movement in the early 20th century by Otto and Maria Neurath. They were trying to kind of educate the working class about the means of production. And they kind of like thought that having very abstract charts and graphs isn't something that is great for people who don't have a lot of visual literacy. And so they came up with these kind of like isotype ideas. So for example, they would visualize here Great Britain, how many people are in Great Britain, by each person here, each icon represents, let's say 100,000 people or 1 million people, and then how much livestock do the producer have. And so we have like 1.5 cows that corresponds to some measure. So for example, what is the red symbol? Like it's 5 million cattle. The pig is 5 million pigs. And yeah, these are all like each unit for the livestock is 5 million, right? And so you get kind of a sense of what that means without having any labels, and you get a sense of the magnitudes. And you also get a sense very clearly that the United States is much bigger, has much more livestock than Great Britain. And so people have studied this in visualization, and they have studied also like, what is more memorable, what is easier to read. And so, for example, this one study here compared these 3 different conditions, like a chart with a fish in the background, which isn't particularly meaningful, right? Then a chart here with a symbol and an abstract bar, and then a chart with these little isotypes. And the outcome is that it doesn't really matter all that much. So you can use just regular bar charts, and you can use these isotypes. It's basically, people understand both similarly well. So basically, you have a little bit of freedom. If you want to do something evocative, you can do any of these isotypes choices here. Of course, it's much easier to just plot a bar than to plot these icons. Any questions, any comments? What would be a problem? Well, I guess what would be a problem if you were to use an isotype? Like, is there any restrictions? Yeah. Yes. So ambiguity in the labeling. Yes. Well, I would also say that one big problem. Do you have a comment? Yeah. Fractional values are a problem. One big problem is that this really works well for countable stuff, right? But it doesn't work well for non-countable things. Like, for example, I can probably do seconds in isotypes, but what would I represent a second as, right? There's not really like a glyph that I could use. So it's great for discountable things, but it gets weird when you have more abstract data. So this is like more of like an infographic design method that you can use in special niche cases, and then it's not a disadvantage, but it doesn't super generalize. Okay, part of a whole relationships is like we talked about pie charts in the design lecture. I'll not talk about pie charts all that much, but the thing that we can use for part of a whole relationships in addition to pie charts are stacked bar charts. And so here we have a Titanic data set, which I'm sure many of you have seen before. The keys that we have here, like these are passengers of the Titanic, and the attributes that we collect about them are what class did the book, did they survive, and are they female or male? No, actually, in this case, it's just those 2 attributes. So we have class and survival. And there's 2 different things that we see here. The one here is the left here shows the absolute values. And so we see in first class, we see there were like 310 or 20 people in first class, fewer in second class, but the majority of people were in third class. And we see that like a lot of people actually looks like survived in first class, not so many in second class, and less in third class, right? So we can get all of this from that chart, but it's harder for us to judge the proportions because, of course, they are on different scales. And so if what we really wanted to look at were the proportions, the fractions, we could use like a proportional area chart, right? And so here we see very clearly that only 38% of the people in first class died, whereas more than 70% of the people in third class died, right? So these charts have a very different message, and like again, it depends on your question which one you would prefer. Yeah, I talked about pie and donut charts, or Max talked about pie and donut charts, and we had talked about them in the D3 lecture. So I'm gonna kind of keep it simple today. These exist. You can sometimes use them if you have not too many segments. So then it's absolutely a visualization that you can choose. But of course, don't there's other design choices that you can make that maybe represents the data better. These charts here, there's nothing wrong with them, right? The tree map is used for hierarchical part of a whole relationship. So think back, I showed you the map of the market one and the London flats last time in the view lecture. And so when we have a whole thing that can be divided up into multiple things and maybe subdivided up, and then the things that are the elements at the end, they constitute something in size, then we can use a tree map. And so for example, here, this would be like sales. We have phones, machines, copiers, accessories, supplies, and so on. So, these are different types. Like, for example, on the right, we have furnishings. And on the left, we have like office, technical office supplies. And so it makes sense to group them. And that's what the tree map here does. We can also use part of a whole for time series. So for example, if we were to ask like how much of a product are we selling over time, as a share of our overall sales. So we can use something like a 100% stacked area chart. But of course, there are some caveats with that. I'll come back to these part of a whole chart or of these for time series charts when I talk about temporal data. Okay, so one big topic to talk about is distributions. And distributions, the idea behind distributions is distributions really give us a good overview of what's in a data set without having to dig too deep into the data set itself. So instead of showing all the data points, we show the distribution of the data. So we have a very compact representation. The negative about it is that, of course, we kind of lose a lot of nuance. So it works if the data is well behaved for the type of distribution visualized. And so we'll be looking at different visualization techniques for distributions and looking at their pros and cons here. So like everybody, I'm sure, is familiar with a histogram, right? A histogram is essentially like a binned representation of a 1D data vector. And so here is like a simple histogram, but this is like a nice interactive explainer. It's maybe a little bit of an overkill for a histogram because it's a fairly simple thing, but let's just be explicit about it. So what we have here is miles per gallon fuel consumption for 32 car models. And so we have kind of like these data values in the beginning. And first we kind of like, we take the smallest to the largest value and we kind of like put them here on this unit interval. And then we generate these bins. These bins, of course, how we generate these bins is more or less our choice. And then we count how many items fall into that bin. And that's how a histogram is constructed, right? So that's very easy. And we can see that there's like, there's sparser values here. And that is why the histogram here is lower. There's denser values here. This is why the histogram is higher. Okay? Any questions about this? Okay, this is very simple. And now it's really not so easy to automatically choose a good number of bins because if you under or over choose the number of bins, it gets tricky. The simplest thing you as computer scientists can do is, of course, make it interactive and let the user figure it out, which is actually a good solution, right? Like I would prefer a tool that does that than one that does some magic and expects me to trust it, right? So like you want to be able to play with your bins if you have an interactive tool. Just some rules of thumb. So you want to maybe initialize your number of bins with the square root of n with log 2 of n plus 1. These are just some ideas that kind of give you some interesting pattern. And just to illustrate these effects, what the chart that I'm showing here is the number of passengers that use public transport. And on the x-axis here, we have age. And so this is binned in 0 to 10, and then something like, or 0 to 9, and then 9 to 18, and then 18 to 25, and so on. And if we choose a different bin here, like for example, 20 bins, we suddenly see some like a completely different effect, right? So we have this kind of like strong outlier here that seems like there's a lot of infants that are using public transport, supposedly with their parents. This dip here, like at like the age of 5 or so, doesn't really show up so much here, right? So this is just like one example, and these artifacts, that can show up a lot, right? If you have a discontinuous distribution, you have to be very careful about how many pins you choose. A different and kind of like actually nowadays probably my favorite distribution visualization are these kernel density estimates, right? Or density plots. And so the idea of these density plots is that they kind of like they show you like a curve similar to what you would usually think of as like a function of a distribution, and they compute this based on certain parameters. And so here's like a very nice interactive explanation. So here we have like raw data plotted on the x-axis, and these KDEs. What we have here is like, here's an example of a KDE, but the KDE, like essentially the height of the point that we have right here, the height of the point we have right here depends on the function that is kind of sketched here in red, right? So the this point here, essentially the points right below that line contribute most to the position of the function, but to the position of that line, but also everything else here contributes a little bit as long as it's under this red curve, right? So this gives you the smooth appearance of the kernel density estimate here. And of course, we can change what function we use here. So for example, we can adjust the bandwidth. And so if we make it a very narrow bandwidth, we will get a very jagged line. And this is now we're probably overfitting, right? If we're using machine learning terms here, this is probably not the actual distribution that we're drawing for, but it's probably overfitted. And so you can play with this, the bandwidth, for example, to kind of smooth this out and find something that is kind of visually appealing and makes sense. And so this is a very similar problem to choosing the number of bins in a histogram, but it's I guess slightly different representation. And then we can also use different kernels. So here we use a Panegyikov distance, but we could also use a normal kernel, or we could use a uniform kernel, which gives us a little bit more of a jagged appearance, or we could use a triangular kernel, right? And so all of these are options. I'm assuming most of the time what you will be doing is you're using some pre-existing library that does this, and so a lot of libraries already have that built in. And then it's useful to think a little bit about what is your bandwidth, what is your amplitude here, and what is your kernel. But usually the defaults are pretty good, and you just want to play with the bandwidth a little bit. And then, of course, you can combine these things, right? So here I'm plotting a KDE plot on top of a histogram or on top of a strip chart, right? So these are kind of cool things to do. One thing that is very commonly used, but maybe is getting a little bit of disfavor, are box plots. And box plots are also known as box and whisker plots. And so what they show is they show the median. They show the interquartile range of the data. So anything between quartile 1 and quartile 3 is in the box here. And then the whiskers here show us the quartile 3 or quartile 1 plus minus 1.5 times the interquartile range, right? So if we look at the normal distribution down here, we see that kind of the majority of the data is actually covered by the box plot, and the middle 50% here are what is shown in the box itself. So the tricky part about this is what I'm showing you here is kind of a convention that is sometimes used, but not every time, right? So you can kind of what your whiskers are is actually up to you to specify. So you have to always if you actually see a box plot, and if you really need to make an accurate judgment based on the box plot, you better look at the labels of the figure and the explanation what it means. The other thing you should do with the box and whisker plots is you should actually plot outliers. So if you have an actual data and not just an abstract distribution as I have here, and you have a data point here, you should plot the point here and here, and maybe here and here, right? You don't plot the points that are summarized with the box plot, but you plot the points that are outside of the whiskers. And these things are nice if you know that you have normally distributed data. Then it's a good choice, right? But if you have not normally distributed data, then box plots are actually not a very good choice. So here is one box plot for 4 very different distributions, right? So we have our normally distributed data at the top, then we have a bimodal distribution. And this is kind of probably the most irregular case here, because we don't see the bimodality at all, right, in the box plot. Also, we don't see the single peak here, or we also don't see a skewed distribution like this in a box plot. So under the assumption of normality, box plot is a decent tool, but if normality is violated, you should use something else. And obviously, histograms or KDE plots would show this data here. And so here's just another example. Well, this is the first thing is about plotting outliers, right? So can my boyfriend come along? I'm not your boyfriend, you totally are. I'm casually dating a number of other people, but he spent twice as much time with me as with anybody else. I'm a clear outlier. And then all the math irrefutable. But so, okay, going back to these distributions, right? So again, for a uniform distribution, a box plot is actually a very bad choice because it's a uniform distribution isn't really shown here. A normal distribution is a reasonable choice. If we have a Poisson distribution, just showing this here, if you have the uniform distribution here, and a normal distribution in orange, a Poisson distribution here in lighter orange, or an exponential distribution. And all of them are really like, everything except for the normal distribution is hard to show. And one thing that you should never, ever, ever do, and I still see people, even in visualization research papers do, is this here on the top. They use bar charts with error bars to represent the distribution. And if you think back, we talked a little bit about this in the design lecture. Why is that a bad idea? Yes, so it kind of like lets you think it's actually like one particular discrete value and not really distribution, right? Other ideas? Yeah.
Like this example on like the left side with the bar graph, or
exactly. That's a very good observation. It's within the bar bias, right? So we assume that the points out of the distribution are drawn from within the body of the bar, which is actually not true. And the uniform example here is very, very extreme, right? So like what we look at is really just the error bar here. And like there's no data value anywhere here along this whole area of the bar chart, right? So clearly this is not a great representation for a data set like that. So, we now, like, back in the day, in the 90s, when all you had was Excel, and Excel could do that, that was maybe an okay representation to use. But nowadays, when we have software to like actually do much better visualizations, you really don't have an excuse to use these bar charts with error bars anymore. Just to re-emphasize this point a little bit. So here, for example, we have like another thing that you could miss is this bimodal distribution here. So we have here a group of controls and a group of patients in some medical experiment. And if we were to have those two values, like if we showed this as a bar chart with error bars, what we would conclude, well, the error bars, they overlap significantly. There doesn't seem to be any effect, right? But if we plotted this as dot plots, we might see that our patients actually split up into two subgroups. So maybe there is some underlying thing, and that intervention works for a subset of the patients, but doesn't work for another subset of the patient, right? So that is something that you should be looking at more closely, but you would completely lose it if you only looked at this in a bar chart with error bars. And so very similar vein is the violin plot. And the violin plot is nothing but a kernel density estimate flipped upside down, or even just horizontal, right? And duplicated, mirrored. And then it's a violin plot, right? So that's the same thing. It's just two kernel density estimate plots that are mirrored. And what's nice is that we have all of the properties of the probability density function here. So we see, for example, when we have a bimodal distribution, like in the green case here, we can't see that in the box plot, but we can very clearly see that in our violin plot. And so here's another example that shows you kind of like the raw data, how it varies, in like from a uniform or like from a normal distribution to these kinds of like very extreme bins. When the box plots remain completely static, but we can see that kind of information very clearly in the violin plots, right? So violin plots are really like, if you want to use a summary statistic, they're a really great choice. And this is like also what I use to report experiments nowadays. Yeah. Yeah, that's a very good question. I think it's mostly an aesthetic choice. And it's kind of like, so that you have this appearance. I don't think there is like an empirical difference. Like people wouldn't be better at judging one or the other. I guess you're imposing a little bit of a reading direction. But yeah, that might be an interesting research paper, right? Comparing violin plots versus just a single KDE plot, giving them the same space, asking people, hey, what do you like better? And trying to see whether they make better estimates, right? My guess is you would see not a lot. But violin plots, somehow they look better, right? I can't really pin it down why, but they kind of like have an aesthetic advantage. Any other questions? And then we can also, for example, we show expected values and uncertainty. Like this is like a little bit different, right? Like if you're drawing from a distribution and you want to plot that, this paper here by Michael Correll and Michael Gleicher studies this, and they also kind of came up with this conclusion that error bars are problematic, and they suggested instead for data like this, when we have a distribution that we want to visualize that this is being drawn from, that using either this kind of like fade out effect here or using a violin plot are good choices here to do that. So you shouldn't use any of those two. That's a good, well, I think this is more of like a caveat. I guess it's a more of like a like a text expression of the uncertainty that you get here, right? What you have here in this example is a predicted value for snow, which might actually be very relevant for tomorrow, right? And so they say like a whatever, my 95% confidence interval is plus or minus 15 centimeters or millimeters or whatever. And so that's what this text here shows, and that's also what these distributions show. Okay. Another thing that you can do, and that is sometimes very useful, is instead of using a kernel density estimate directly, you can show the cumulative kernel density estimate, right? So here we have 2 KDEs on the left and the same data shown as a cumulative KDE. Let's talk about the data first so that you know what we're talking about here. This is also like a famous machine learning data set. Bill, like how much did patrons of a restaurant spend for lunch or dinner? And what we can see here, lunch is the blue curve, and dinner is the orange curve. And what we can see here is that maybe the total bill amount for lunch it peaks a little bit lower than the total bill amount for dinner. Okay, and we see that there's maybe like a longer tail for dinner. So there's like a few people that spend $60 on dinner, but there's like only very few people that spend even $50 for lunch, right? So that's kind of like the data set that we see here. And we can read this from this KDE plot, but we can also plot this as a cumulative KDE plot. And so what we have here is the total bill amount versus the density. Like basically at which point here, if you intersect the 0.4 line here with the curve, then you can read off like 40% of all bills for lunch are $13 or less, right? That's what you can read from this chart. And this is very nice to compare because here it kind of like, what we see here in this particular KDE plot, it's not quite as evident as it is in this cumulative KDE plot, right? So we can very clearly see that there's more people that spend a little bit less for lunch than and people for dinner tend to spend a little bit more. And we see it's like a slightly flatter curve, right? There's very few people. For example, we can say 90% of people spend less than $30 for lunch. And this is exactly what is super easy to read from these cumulative KDE plots. What percentage of bills are less than 20, for example, right? And we can read this in both ways. So we can say like 90% of my population have a bill of less than, for lunch of less than 25, right? Or 30, something like that. So this is very easy to answer these particular questions. And that's a chart that I think is underused, and it takes a little bit of getting used to. I wouldn't use this chart alone, right? Like I think it's a little bit too confusing for people initially. So I would combine this maybe with a KDE plot or with a histogram and just explain it a little bit if I were to use this in a figure. But once you actually explain it to people, you can read off things that are hard to read off elsewhere. And then you can use an empirical KDE. And that's just a simple version of the KDE plot, the cumulative KDE plot. You don't have to do anything like converting it to some kind of like distribution function. Here, we simply just plot the points, right? So we plot the observed points instead of the function. And so this here is an example of which like countries get some kind of economic freedom summary index. So how freely can people like invest and run the economy. And each country here is one dot. And you see that they kind of like aligned up. So the first country here is like 0.1 1% or 1% of all countries, right? And then we add the second country here, and it's basically just lined up. Each country is like one line up, and then we plot the summary index on the right. And this is like now we kind of get the same impression that we get from the KDE plot, but these are real values, right? They're actual values, and we can make many of the same judgments here as we can for the cumulative KDE plot. So what percentage of countries have a summary index of less than 6? We can very quickly look up 6, like 20% is the answer, right? What is an approximate percentage of the countries that have a summary index less than 8? We can look that up. It's like actually, well, almost 95%, or yeah, more than 95% of countries have less than 8, right? So very useful plots for certain situations. Yeah.
So for that last one, they have to be sorted by lowest.
Exactly. You would make that, right? If you plot that, you would take the data vector, sort it low to high, and then just plot it. And so this is trivial, right? There's no math at all in this, and it's a very powerful plot. And here's the summary, which is like I found on Twitter recently. And these are all done with Seaborn, which is like a Python plotting library, right? And so you can use all of them here. At the top, you have our distributions. Then we have the strip plots, which I didn't explicitly mention because it's just a raw data visualization, right? The strip plot here, and then we have the B-swarm plot. The B-swarm plot is very similar to the strip plot, but instead of using random jitter, it makes sure that every point has its unique position, so you can't bound it, but there's no overlap. So that's the difference between those two. A RAG plot uses transparent lines, and then as the lines overlap, you see these density patterns. We talked about KDEs. This is the same KDE, but instead of having a curve, we're just color coding it, right? That can be effective if you have a narrow area to draw. Cumulative KDE, empirical CDF, this is what I just talked about last. Histograms, box plots, box end plots, which is just like a variety with more statistical nuance to it, I guess. The Tufty quartile plots, which I probably wouldn't use all that much, but these are just like, yeah, some variations on essentially a box plot here that you could potentially use, and these are all supported by libraries like Seaborn nowadays. So really no excuse to use box plots. This is an example from a paper from my group, and this is how we now report statistical results. So for example, what we're doing here is we're showing accuracy scores and time for 2 different tasks. So we have our accuracy scores here, and then our times. And what we have 2 different conditions, NL and AM. And we see that, like, in the AM, we have kind of like a bimodal distribution. This would be really hard to see. And then we also show 95% confidence intervals here. This is kind of like, a useful metric to kind of like judge how likely is this to be a real effect. And then we also report on effect sizes. We also report on effect sizes, and we also show p-values in this case. But yeah, like that's a very comprehensive statistical representation that uses both visual communication, shows you the actual distribution, shows you the 95% confidence interval, shows you statistical significance, and shows you effect sizes all in one, right? So like we built this kind of like little library ourselves where we just throw in distributions and spits out these charts, and they're easy for us to interpret, and they're also useful for reviewers and readers. Okay, so the trouble with distribution visualizations is that they summarize, right? And whenever you summarize, you lose something. And this is a technique. What you see here is called like a lineup technique. And people have done this in various things. So basically, the idea is you show a human something, and they have to pick out one that is different from the others. And if they can pick out something, then there's like, you can test something. What the point of this lineup is take a look. Let's first look at these plots here. Is there one that stands out as odd to anybody? Which one? Middle left? Middle right. This one here? Yeah, that looks odd. Anybody else have any opinions? Yeah? Middle left upper. This one? That's too perfect. So what do we, okay. And now let's look at the chart on the right with the dot plots. Anyone that stands out? Yeah. Exactly. And those two charts show the same data. And so in this case here, like everybody agree that this here is an outlier? Yeah. We couldn't see that really here, right? But in fact, this one here is the outlier. So this one and this one here are the outlier. These are 19 charts. 19 of these charts, except for this one, are random samples from a Gaussian distribution. And one chart has 20% of the samples with an identical value. So these are actually exactly the same value. For example, if you had an error in your data collection pipeline and somehow your function that collects the data gives you back some integer if something goes wrong, right? This is like, this would be what happens, right? And this is almost impossible to spot here, right? This doesn't look much different from this here, for example. We talked about this, or from many others, because, you know, these smoothing functions, they kind of like, you know, they hide these details, and also the random drawing is of course not perfect. And so especially if you have smaller sample sizes. But again, the chart on the right isn't the perfect solution either. And so this paper here is about detecting data flaws. And so generally data flaws are tricky to spot with aggregate visualizations. It really depends a lot on the bin size, on the kernel type, on the bandwidth, on the visualization choice. And these guys, they looked at 4 different types of data flaws. Well, actually, one the original distribution, then a gap, then the effect of outliers that are distributed, and then the effect of spikes, right? And in the end, you know, as always in visualization, unfortunately, there isn't a clear answer. You always have to look at multiple plots to make sure that you don't miss anything like it. But certain things like the spike is probably easier to notice in the dot plot than in the other ones. This is what we just saw earlier, right? And similarly, like maybe, you know, I don't know, the gap might be harder to spot in the dot plots. It's a little tricky. The paper is interesting to read, especially like, you know, it kind of questions, it helps you question a little bit on how much are we trusting all of this stuff, which is always a good question to ask yourself if you look at data, right? So definitely make sure that you also look at raw data and not just the distributions. Look at your data in many different ways. Okay, any questions about this before we move on? Okay, so next one, deviation. Deviation is about, you know, how is something different from another one? Now, like we're going back to the Financial Times classification here. Like we had distributions, and now we're moving on to deviations. And this is going to be super short because essentially it's just, you know, show a bar chart or a line chart and a 0 point. So you can have like a diverging bar chart. You can have this juxtaposition of 2 variables, for example, male, female, or you can have like surplus deficit below and above a line, and you can always use color to reinforce these differences to kind of like have a redundant encoding. And you can have the same thing with a line chart. So I don't have much more to say here because this is just like magnitude, right? But with like something that goes across the axis, but just for completeness sake. Then I want to talk about change over time. And change over time, of course, we have our familiar line chart. And the line chart is kind of like the standard visualization for temporal data. It's simple, it's familiar, it's accurate, it's fairly scalable, especially if your lines move in concert together in some ways, right? So this here is this this kind of chart about the unemployment rate in 50 states in the United States. And what we see here, like this is like we have 50 data values, and very nicely we can see these trends. We can see that there are some outliers. So, for example, the Detroit area in Michigan had like higher unemployment rates, even when kind of like the economy was doing well. And then other things like the Maryland area around DC, for example, always had very low unemployment rates, right? And so we can see trends, we can see outliers. This all like moves together because the data is kind of correlated, of course, because we are all in one economy. we can see these nuances. Like a little note, and I might have shown this before, but this is like a very nice implementation where, as you see, my mouse here, let's zoom in a bit. My mouse here moves freely, and I'm brushing different segments. And I'm always brushing like the line that I'm closest to, even if I don't perfectly pick it. And the way to do this behind the scenes is by drawing these Voronoi diagrams that kind of like identify the point where it's going to be highlighted. So you see that this huge cell here, as long as I don't leave this cell with my cursor, I'm going to stick with this one point. And if I go over here, it moves to this next point here. So that's kind of how this is implemented behind the scenes. It's just a very cool technique. It's easy to do in D3. We'll be talking about how we construct these Voronoi diagrams in the aggregation lecture. Of course, I can also do these like with dots, but you know the difference here, if I have a dot like it's series like this, is if I have two series of that, I couldn't really tell them apart anymore, right? So like the lines here really make sense to identify the item, and so usually that's what we use. So now coming back to the stacked area chart, so we can definitely use stacked area charts. The tricky thing about stacked area chart is like basically the things that you can read is mostly like the overall shape and the shape of the lower curve. But the shape of the second and the third curve are really tricky to read because you have to mentally account for what's going on below it, right? And so you have to use this with a little bit of caution. You can definitely tell, for example, that the brown area here shrinks between here and here, right? But it's not completely obvious. And so you have to be cautious about this. You could use a 100% stacked area chart. Here, like the upper and the lower one are easy to read, but again, the middle one is tricky to read. And if you have more than three, this will be a compounded effect. Little quiz here. We have the market share of product orange, product green, product blue. Anybody want to describe it, like, let's say, is blue declining? Is blue rising? Is green declining? Is green rising? Is orange declining? Is green rising? What do you think? Yeah. Green is slightly. Can anybody else think that is true? False. So the funny thing is, and you're almost right, but the funny thing is that what we tend to do here is we tend to look at the lowest, the distance here, right? This is what we mentally judge. But what we should be actually mentally judging is this here. And so now if we plot this as a line chart, we see that green is actually slightly increasing, right? And so that's kind of like a tricky effect. And that's a perceptual problem that we have here, right? Because it's, for us, it's very natural to see, hey, we judge the line here, the tangent, the kind of like the normal to the tangents here, and then we look at the normal to the tangents here. But what we actually should be doing is look at the y-axis value, right? And so that's why, another reason why these stacked area charts are a little bit tricky, and always use them cautiously. Yeah. Yes. You mean this? You mean this is coding more or less? Yeah. Oh yeah, this is always a choice, right? If you can always separate them out, like instead of having 3 lines here in one chart, I could have 3 charts here with a single line, right? That is something that you can definitely do. I think, you know, this is a constructed example, right? This is an extreme example where I can point to like, okay, you didn't realize this nuance. Overall, these charts aren't completely useless, right? They are like, they still give you a good impression, and people still use the fancy version of the stream graphs if you, for example, if you want to visualize movie popularity over time for genres, you don't actually care so much about the precision, right? It is an evocative chart type, and so you can. It is not unreasonable to use. I just want to give you kind of like the pros and cons of them. So like you shouldn't completely avoid a chart like this. If you really want to show the proportions over time, why not, right? And you like, if I were to design a visualization that I want to put in a newspaper, what I would do is, if I want to use the stacked area chart, I would plot it as a line graph. Then I would kind of double check, is my data fairly represented in the stacked area graph? And then I might use the stacked area graph, right? So here is like a different example. Here we show this as stacked bar charts versus stacked area charts. And so what we are showing here is sales of weapons, miscellaneous revolvers in gray, shotguns in light blue, pistols in orange, and rifles in blue. And kind of like, I guess what we see here, this is data from 86 to 2010. And what we clearly see here is that, well, it looks like around 2010, sales of weapons generally peaked. Now, can we tell what the driving factor is here? Like, which of these types of weapons is being sold the most? Orange, yeah, pistol. So indeed, we can tell it, right? So if we plotted this separately, though, I think it's a little bit of a different story, right? Because here we see that this rapid rise of pistol sales, right? That isn't completely evident from this chart here. So it seems like a much more pronounced effect here, that any time since between 2004 and 2010, this really shot up and even overtook the sale of rifles, for example. So, you know, again, pros and cons. The overall trend is harder to see, of course, in this chart here. But if we want to look at the outliers, we can definitely see this better in this chart here. And another time series visualization are spark lines. And spark lines are small, typically unlabeled line charts that can be embedded in text or be part of a table. And you, for example, see this frequently. I think Bloomberg or some other financial website does this actually on the website. So whenever they mention the company, they show their most recent stock value in like a little embedded line chart like this here. And you can do this in a table. And typically, you know, here you don't have, these are kind of like, they don't give you precise values, that you don't have legends, you don't have scales, but they give you kind of like an idea of the trend. And so this is kind of like a cool idea that sometimes can be useful. And if you think back to this focus and context techniques, I could easily imagine a scenario where you zoom in here and then suddenly start adding in axis, right, as you zoom in more. And one problem with these like little line charts is that they get very dense. And so to address this, people have invented these horizon graphs. And so what like horizon graph does is, let me actually show this tool here. One of my grad students has implemented this. And so a horizon chart essentially takes a line like you see here on the right, and then slices it up according to the bins and then stacks it. And so instead of having this like large curve here, it kind of moves it to the center and compresses it and shows you the contours here, right? So you can kind of see that things have risen here, and then they fall down here and they rise up again, but you need very little space, right? So you can actually show this in a very compact representation. You actually, strictly speaking, you don't need the colors. You could do just with the contours, but the colors are of course helpful. And you can also do other things to this. You can say, hey, mirror my negatives, and then I like, you know, this would be another option. Here I have more amplitude to use, it's kind of like easier to read maybe. You encode this the up and down by color. You can choose to include the bin lines or not. Here you would actually really need the color. And then you can do like other parameters here. You can play with this the way you want, right? So yeah, horizon charts, and people have run studies, and they've actually shown that they are just as effective at reading data values as larger line charts. And so definitely an interesting idea worth considering if you have some very compact representation, for example, like a stock ticker or something like that you want to do. And then sometimes, like the problem with horizon graphs can also be that you have outliers that kind of screw up your scale, right? This is like not an uncommon thing. And this is something that we encountered in the project when we were like looking to visualize air quality in Utah. As you know, air quality can get really terrible, right? And so these outliers really ruined our scale here that we wanted to look at. And so instead of horizon graphs, we kind of like, we decided also because we figured it might be a little bit easier to understand to do these clipped graphs. And so here what we show is we show a redundant encoding of line height and of color. And so like a standard clip graph would look like this. And so you wouldn't actually see that peak here, but on interaction, you can render that peak, right? So you can temporarily overplot something. And so we played around with this here in a project where we looked at pedigrees based on the Utah population database and on looking at suicide and whether air quality events correlate with suicide. And we used these kind of like clip graphs here to look at NO2, mean NO2, max NO2, PM2.5, and so on. And so you could kind of like, you would see this as like a color distribution, but if you hover over it, you kind of get the full line, the enlarged line chart, so you can see the particular peaks and inspect that in detail. And we did this because we wanted this to embed this into these large family pedigrees here, into these tables here, and so we had very limited space. Another way to visualize temporal data are these connected scatter plots. And that connected scatter plots are great when you have two variables over time. And typically, if you wanted to do this with line charts, you could do only one per chart. But like you could only pick one variable for a chart. But if you use a connected scatter plot, you can actually show those two variables over time. And so what we have here is well, the data here, I think, is the relationship between the top 0.1% and the bottom 90%. Like, I'm actually not sure what this data was, but it's probably some income distribution. And so what you see is we started out in 1917 here at this point, and then over time, it went into this kind of like extreme here, then it went to the middle, and then in the 2010s, it went back up again, right? So this is kind of like a cool chart. If you have two dependent variables that you want to show next to each other. The problem is, also this is what this text here refers to, is you can't do multiple of those in one chart, right? It gets really cluttered. Like a line chart, you can do many. For those ones, you really should limit yourself to one. And there's good examples from newspaper stories that do that, like you see here on the right. And here's like a blog post by Alberto Cairo, who writes a lot of visualization books where he analyzes these connected scatter plots. The other thing that you really want to do for temporal data, of course, are heat, like calendar and calendar charts and calendar heat maps. And because, temporal data is very often seasonal. We expect, for example, driving patterns to be different on weekends, driving patterns to be different on holidays. And so bringing that context is very useful. And that's why we have these calendar charts. And for example, D3 provides templates for these calendar charts. And this is like a chart of traffic fatalities in 2008. And we can see a very clear weekend pattern, like Sunday and Saturday have more fatalities, and also Fridays have more fatalities. And we can also see some seasonal patterns, right? So here, like the holiday driving season in July, we have more midweek accidents. And then here we have kind of like Halloween, and then like the Christmas holidays, right? We see these patterns, and we can associate them with the time of the year. And then the chart here on the right shows us a heat map over years for states. And this chart actually won an Information is Beautiful award. This chart is supposed to illustrate the effect of vaccinations. This is about measles data from the 1930s to 2010. And you have this kind of like color legend on here. from 0 to 4,000 cases, and then you have this listed by different states. And then the big thing here is that the annotation here, the vaccine was introduced in 1963, and the big vaccination campaign was ongoing, and we see this very impressive drop off in the cases, right? So that's a cool chart, and it won an award. Anybody have any gripes with it? Yeah, I don't know about the anti-vax movement in 1967, but any other problems you have? Yeah, I feel like the color scale is cheating, right? It seems like my sense here is that the color scale is chosen to, impress and to make it colorful. It doesn't seem to be like a rationally justifiable color scale to me. I don't really know. And so, aesthetically interesting, good story, convincing. It draws people in because of its richness and color. But this is the same chart. Instead of showing the data for individual states, I'm just showing it aggregated for all of the United States. And so, this is, clearly we can see the effect here just as well. We have the same problem that we talked about a lot, right? Which is the more interesting chart. Would this get people's attention? I guess one thing that I didn't realize when I looked at this earlier chart was this extreme rise between 1940 and 1955, right? That isn't something that is evident here, right? It's kind of like obscured by the color map. So it's maybe even like, this is probably the better chart. Do you really need to know the differences between states? I guess not really for making the judgment, right? So it's more of like a design choice in some ways. Okay, the last chart to talk about time series is the waterfall chart. And this is kind of like an interesting chart. It's maybe a little bit niche, but it's a great way to show the evolution of a part of a whole relationship. And what this particular waterfall chart here visualizes is the history of the space, like actually land space in the European Union. And so started out in 1957 with the Treaty of Rome. And we have here the core European territory in dark green, and then outermost regions, which are kind of like European colonies that belong to European countries, but are outside of what we usually would geographically call Europe. And then you see very quickly these outermost regions, Algeria became independent, which was part of France, right? And so like the size of the EU actually dramatically dropped here because Algeria became independent. And then Denmark, Ireland, and the UK joined, and then there is, I'm actually not completely sure, but well, actually this is Greenland, right? So here we have the big, Greenland is like large by area, and that's part of Denmark. And then we have Greece join, and then Greenland becomes autonomous and is not part of the EU anymore. And then Portugal and Spain is being added, and then East Germany is being added to Germany, and then Austria, Sweden, and Finland joined, and then Norway doesn't join, rejects to join again, and then all of the Eastern expansion happens, and then Romania and Bulgaria are added, Croatia is added, and then the UK leaves Europe, and now we are here, right? And so it's kind of like this nice evolution of charts. We are always taking the previous position and going up or down with the next bar chart from it, right? And so if you have the right data, this can be a very engaging chart to read. Great, so the last couple of minutes, and I'll just hand this out and let you play with it, and then we'll discuss it at the beginning next time. Here we have, and in this case, like I have a printout here, but it's useful to play with it because it's a 3D chart. It's a 3D yield curve, and you can play with it. You can zoom in, you can zoom out, you can go through different steps. And so look at this, talk about it in the group, bring the sheet back next time, and then we'll discuss it at the beginning of next lecture. I'll be around to answer any questions you might still have, but we won't get to discussing it today. Yes.
Like you think about yourself that
I'm sure there's some more floating around somewhere. Any leftovers? You didn't get any? Can you guys share? And it's also, there's a link to the document so you can access the Google Drive. Well, I'll put it up on the projector. I don't, but if you go to this top link here, you can get to the sheet. Yeah. Okay.